Hey, hi there. So, welcome to this session on UVM phasing. These are the sessions where we are going to do the deep dive of each of these concepts. So, let's quickly jump into the agenda. So, agenda for this session would be that we will look at why do we need the phasing mechanism, and we'll look at what are the UVM phases, then how does the overall test flow start top down, and how we enter into the phasing. And then there are three major phases that are involved. Of course, each of these have sub phases. So we have build phase, in which an entire environment gets built and connected. Run phase, where the real action of stimulus generation, checking, functional coverage gathering, all of it takes place. Then cleanup phase, where we extract various information about test execution from different test bench components, and report the statistics about the test as well as whether the test has passed or failed. And then we have a couple of special topics which directly relate to the phasing mechanism, called end of test and phase jumping. These are important. So end of test helps us decide when to end the test, right? At very simple, we want to ensure that we have generated all the stimulus, and all the responses for that stimulus have come back from the DUT, and test bench has had a chance to look at it, right? So that's when we want to end the test. And then there is a concept of phase jumping, which is an advanced concept. We are not going to be looking very deep at it, but we'll introduce you so that you are aware of it, so that as and when the need arises, you can go deep into it. It's mainly used for handling the dynamic resets in the environment. Dynamic reset meaning that when you do the reset in the middle of some data transfer, right? So those type of scenarios when you want to create randomly, right, then the phase jumping is a very useful mechanism. I should not say very useful, but it's one of the mechanism to implement it. So we will briefly look at that. However, it's not a very popular topic, and it has its own nuances, so one has to do it carefully. So the first question, as usual, we start with why. So why do we need phases? So we have seen both the module-based test benches, and now we have looked at a bit of class-based test benches in the SystemVerilog, and we are looking at the UVM based test benches, which are also class-based test bench. So why do we? So with that context in mind, let's understand why do we need the phasing mechanism. So in the module based test bench, what happens is that the entire hierarchy of whatever the modules that you are dividing your test bench and building it, it all exists, and it's all connected at the beginning of simulation, so that there is no possibility that you send something without something being constructed, right? So your all the modules, you need to instance them, and all of them are connected. You are doing static port connection, so there is no possibility that you started your test and you sent a simulation and something component was not constructed. You have null object handle reference. Nothing of that sort is possible in the static based. And also the module based test benches are like simpler, they're static, and the in terms of the flexibility, they are limited flexibility, and the reusability is also very limited, right? That is the challenges with the module based test benches, and that is exactly the reason why you don't really need phasing. I am not saying that you would not benefit from still having the concept of phasing, where you divide your test execution in different parts and do it, but even in the absence, it's not gonna like affect it too much, right? So that is the nature of module based test benches. But when you come to object oriented test benches, so the test bench hierarchy and the connection between those hierarchies don't exist, right? And it all gets created dynamically. And now on the top of that, what we are trying to accomplish as a part of UVM is that we want the test intent and test environment to be separated, and then the test being able to structurally configure the test bench as per the test intent, wherein the hierarchy of the test bench not only gets dynamically generated, but gets generated as per the custom requirement of test, right? So, and in order to do this, we need some sort of a synchronized flow across the test bench components to provide this ability that we dynamically construct the test bench based on test configuration, and then we have the separation between the test intent and the environment, and still everything works together, right? In order for that to happen, we have, like, the idea is we have decoupling, but still we need everybody to sort of do it at the right time and help test accomplish its intent, right? So that is where you need the phasing, right, which provides that synchronization, and it provides the consistent test bench execution flow in order to accomplish this objective. So phasing, in a nutshell, is nothing but set of functions and tasks that are executed in certain order by the UVM root. Okay. Now, what are those set of functions and tasks? So we have so there are two ways to look at it. One is at a big picture level. So we have these three phases. So we have a build phase, we have a run phases, and we have the cleanup phases. Okay, so and build phase is where actually the test bench is configured and connected, and then run phase is where the time is consumed by running the test cases, where as we talked about, actual stimulus gets generated, checks gets performed, and then the functional coverage gets gathered. And cleanup phase is basically the results of test cases are collected and reported. Okay, and the way this works is a UVM component base class contains the virtual methods for each of these phases. So except the run phase, right, which involves all of these, except these run phases, rest all are functions. Okay, so they're all functions that they don't consume any time. It's only the run phase that consumes the time, so it's made up of tasks, and we will see that rest all of them are functions. And the expectation from the user is that any UVM component, any UVM class that extends the component that belongs to a component hierarchy, right, it could be either extending from UVM component or any base class that's extending from UVM component, can utilize these functions and tasks. So they need to populate the code, that whatever the code that you intend should happen in that particular phase, the user can go ahead and populate it over there. Now, one key thing that we need to understand is the rest of it is, in a way, it is clear that we have. So like one way the whole phasing thing flows is we start the build, and then we come to connect, and then we do the end of elaboration, and then that's the end of build phase, and then we do the start of simulation, and after doing the start of simulation we have the run phase, and after finishing the run phase it goes through the cleanup phases, which is made up of extract, check, report, and final. And note that it's not mandatory to populate all the phases in all the components. So whatever is relevant for that particular component, those phases can be implemented, and whatever that you implement gets executed in this order. This is what you need to really understand, that whatever you implement gets executed in this order. Now, one thing that let's address it before we go further. So run phase, if you see, we have two hierarchies. So what this means is that as we have talked about in the previous, like as a part of UVM introduction, that UVM has evolved quite a bit, right? And then because of that, it has gathered multiple mechanisms in place. So this one we have about 9 phases. These are 9 like a primary phases. So 4 over here, 5th one, and then these 4, right? So we have 9 phases, and this is one way that the entire test execution can flow. And these subphases of the run phase actually run parallel to the run phase. So what this means is all these tasks are ordered in a way that they run parallel to run task. Okay, and in each of these tasks, again, you can be rising and dropping objection, and based on that it moves from one subphase to another subphase, right? Like I drop all the objections of pre-reset, it moves to reset. I drop all objections in the reset, it goes to post reset, so on and so forth, right? And we will look at it briefly, that what needs to be done in each of these subphases. But what you need to understand is that you can either run phase as a single task and accomplish these functionalities in the same task, or you can use these sub phases which has a finer granularity of the run phase, and you should not use both of them. You should use one of them, and this mechanism wherein it gets divided into reset, configure, main and shutdown. These four subphases, and of course the pre and post versions of them. So in total 12 subphases which provide the finer granularity of the control of the run phase. So you have to pick one of them. You have to either use these or you use the run. Okay, and run phase is the concept that was introduced in the UVM, whereas this multiple subphases is a concept that is carried over from the OVM, but it's still present in the UVM. But the general recommendation that we have seen is that you stick with the run phase, and only under very special conditions where you really need it and there is a very strong case for it, you should be using the reset, configure, main and shutdown based phasing mechanism within the run phase. And what can be done in each of these subphases we will look at as we proceed in this session. We will quickly refresh the UVM object hierarchy. So we have UVM object, we have report object, we have UVM component, and the component is the base class hierarchy in which all the phasing virtual tasks and functions are implemented, and any base class that's extending from the UVM component will have access to this, right? So you have UVM test, or you can have the UVM env, you can have the UVM driver, UVM agent, all of these, right? So anything that is extending from the UVM component will have access to the phasing functions. And as I'm showing a snippet of the UVM component base class, which is extending from the UVM report object over here. I'm not showing all of it, but I'm showing some key things. So you can see that all these phasing functions are declared, right? So you can see that extern virtual function void build phase UVM phase type is passed as an argument. So build phase, you have connect phase, all of them are virtual functions. Then you have start of simulation, run phase, and then the reset, configure, main and shutdown, which run in parallel. You can see all of them are again tasks, right? So you can see all the run phase related methods are all tasks, and again you come to the reporting phase. I'm not showing pre and post due to lack of space, but they are present. You can always go open the UVM component, the base class hierarchy, and look at them just to get a sense of it, that how they have been defined. And then we have this extract, check and report and final phases. They are also again external virtual functions. So always looking at the conceptual diagram and then correlating to code gives that sort of clarity that what we are talking about is not just in a concept form, it exists real. And what we do is, so we extend UVM component and put in the functionality within these the phasing functions and tasks. So we look at now next, how do we do the entry from the test to the phasing mechanism. We will start how the test begins, how the control comes into phasing, and how it goes through various phases. And then towards the end of this session, we will be seeing how the test ends. So a journey of test from its start to end with the intermediate, and how that sort of interviews with the phasing mechanism. That's what I think we'll be looking at. So let's get a big picture in. We will start the sorry. We will start the test with like vsim, and then we'll have work.tbtop, and then we'll be passing plus UVM test name equal to my test. Don't worry about the simulator level details. What we are really interested in is that the UVM test from the command line, we start it by passing this command line argument called plus UVM underscore test name equal to, in the string form we pass the name of test. And then in the once we do this, then let's look at what happens in the Testbench source code. So we have module top, we are importing the UVM package, we are including UVM macros, and then in the initial begin and end at some place in your Testbench top, you would be calling run test. Of course, you can run the same test by passing it directly as an argument to run test, but when you do this, then in your compile you are stuck with always running this test. So doing this way is recommended. I'm just showing you here the possible ways to do it. So don't pass directly the test name over here, but this is possible. So when you do this, when you call run test and my test, what happens is the control flow starts from the point wherein the UVM in the UVM root it goes to, so this goes to, as we have seen, it goes to UVM globals. We have this task. From this task, the control gets passed to UVM root. UVM root again has this function called as run test, and while that is happening, what happens is that the UVM so we are calling the this particular UVM method from the static part of the test bench, because we are invoking it from the module, and then it will be passing through the globals, and from the globals it will be passing through the UVM root. And before doing that, what the UVM does is it constructs the top, right? It constructs the top of UVM and which is also called as UVM root, and it also creates a UVM test top. Okay, these are two different things. So UVM root which is also called as which is created in the handle called UVM top, and it also creates another handle and object called UVM test top. And in the UVM test top, whatever the test name that we are passing gets instanced. Okay, so that particular test gets instanced through the factory, because in the UVM test we would have called UVM component utils and we would have registered that particular test. So through that it does name to data type mapping, and using that it creates the test. Okay, so that's what it does it in the through the factory. And then once we do that, it comes into the UVM roots run test task where the phasing gets launched off, right? So the phasing will be launched, and once the phasing is launched, the first thing that it starts executing the build phase, right? And then like to remind you that the phasing is only applicable to all the classes that are derived from the component hierarchy. So component hierarchy means either a UVM component or an base class that is deriving UVM component, and then we are deriving that particular base class. Like for example, if I am deriving UVM env, UVM test, UVM driver, UVM agent, UVM monitor, UVM subscriber. So if I am deriving from one of them which are in turn deriving the UVM component, then for all of them the phasing is applicable. So we will start off with the build phase of all the UVM components, and it is called top down. That is, you first do the build phase of your test, and then the test does the build phase of environment. So you start off with the build phase of the test, and then it will execute. Then once it has ended, then it will check if there are any more objects which are derived from the UVM component have been created. So what happens in your test when it executes towards, so you would have created a UVM env type of an object, right? So after executing the test build phase, when the phasing engine looks for if there are any more objects available which are derived from the UVM component hierarchy, it will find an environment, right? So and then it will go execute the environments build phase, and once the environments build phase completes, it will go and find out if there are any new objects created with the which are derived from the component hierarchy. At that point it will find various agents, for example, right? So and then it will keep doing that, so on and so forth, till it does it for the agent, and then maybe it will come for the driver. And once the driver and all those leaf level components are, the build phase executes, there are no more new components created for which the build has to be called. So once this way, when we come from top down, and once we have finished building all the leaf level nodes, and the phasing engine finds that there are no new objects available which are from the derived from the component hierarchy, the phasing moves from the build phase to the connect phase. In the connect phase, the similar process is executed, which executes bottom up. Okay, so connect phase we could have executed either way, just the methodology is doing the bottom up, because it is okay as long as the two components that we intend to connect are available. We can connect them in any order. Okay, it doesn't matter how you connect, but they should be available. But while doing the build phase, we have to do top down, because as you know that for the component, one of the other functionality, there are two functionalities for the UVM component. One is establishing the object hierarchy, and second is doing the phasing. So for establishing the object hierarchy, what that means is we need to know the parent for every children, right? So it becomes easy if the parent is created and then the child is created. because every child then will know the parent. So that is one of the reason that the top down works better. But the connect happens bottom up. So from the leaf level, it will start off. If there is a connect phase in the driver, monitor, subscriber, and then it will move up to the agent, and then it will move up to the environment, and then it will move up to the test. And once the test is done, there is nothing left. So that is the end of the connect phase. So for the build and connect, we are able to see that it goes through the entire hierarchy, one top down, and then it comes bottom up, and once it has come bottom up, it knows that there is nothing more left, right? So that is when that particular phase ends and moves on to the next one, because for these phasing, what's important is to know when it enters, when it exits, right? So for example, connect phase exit is at the end of the build phase, and the connect phase exit is when it has reached the top, right? When it has reached the test top, UVM test top, which is the current test that is running, the connect phase is over, right? So it moves on to the next, to the run phase. Now in the run phase, as I have talked about, there is the run phase task that starts running. Along with that 12 subphases that we had talked about, those also get launched separately. So both of them start running in parallel, and you are recommended to use one of them, right? Don't use both of them. Okay, so it is only one of them that you should choose, and typical recommendation is to just stick on with the run phase task instead of going through that the different granular way of doing the run task. But anyway, so either of the options you choose, what you have to remember is the run phase gets launched parallel. So for all of the components, the run phase is forked off. If you remember our FIFO test bench, we had forked off the run task of all the test bench components we had. Similarly, the run phase of every UVM component gets forked off in parallel. Now, one question that comes is that when does the run phase end? Because all of them are running in parallel. In the build or connect, we had a clear-cut order that we are traversing in one direction, and when we hit the end, when we hit the leaf, we are exiting build. When we hit the top, we are exiting connect. So it was very clear. But in the run phase, everybody is running parallel, right? And if you remember, in the most of the components, they will use the forever loops. So how do we detect that when is it done? That is where the objection mechanism has been provided. Objection mechanism is only applicable to task phases, and the only task phase is run phase. So we call task phases because we have those 12 subphases as well. That's why we call task phases, but in essence it's the run phase. So you raise the objection and you drop the objection, and when the raising and dropping of the objections can be done by any component. Okay, any component can raise objection and drop objection in the entire test bench hierarchy, and its generally recommendation is that you do the raise and drop objection in test for figuring out whether the stimulus has completed, and in the scoreboard to figure out the response, all the response have been gathered, right? So those are the two components in which it is recommended. Rest of the components you should ideally be not doing it. We will talk about a little bit more about this guideline towards the end of session. But if many components have raised the objection, then the run phase will continue. It will means the root will not terminate the run phase and move on to the next reporting phase unless and until all the components who have raised the objection drop the objection. Only after all the components have dropped the objection, the root moves phasing from run phase to the reporting phase. And then the functions that are provided in the reporting phase get executed in the order that is provided. So, and all the reporting functions as well execute in the bottom up fashion. Okay, so that is a detail. We will look at it, but this is the overall idea. So we looked at how the entry point starts from running the simulation, passing the test name, it comes to the run test, goes into the UVM globals where this particular task gets called, and then from there it goes to UVM root, end root, the test gets created through the factory, whatever the test name that we have passed, and then the phasing gets initiated, and then first phase will be built. All those 9 phases that we have, 9 main phases that I have shown, they all execute in order. So it starts from the build, which executes top down, goes to connect, which executes bottom up, then run phase of all the components starts running in parallel, and any number of components can raise objection, and the run phase holds till all the components have dropped the objection and the total number of outstanding objection goes back to 0. So when it goes back to 0, it moves to the reporting phase and all reporting phase functions gets executed. So this is how the phasing mechanism works. In the next few slides, we will look at what needs to be done in each of these phasing tasks or functions. Okay, we'll start off with the build phase, which is the first phase. So build phase constructs the test bench hierarchy from top down, and for hierarchy parent is needed first. This means that parent is always constructed first and then their children. That's why it runs the top down, which we have already kind of briefly looked at it. The build phase is a function of UVM component and involves creating instances of various child UVM components, and such as following using the factory. So how do we do it? So you have test and then the environment, and then various subscriber, agent and scoreboards get created. Again, within the agent, a sequencer, driver and monitors get created. Okay, so now what I am showing you here is I'm just showing you from the simulation log. So you can create small, like within the test bench, within each phase, within the build phase of each of these components. Like for example, in the tests connect phase, I can say I'm entering the connect phase. In the environment, I can say entering the connect phase. So when I run, I can just look at the order in which it is called to confirm that whether it is really top down or not. And this is the log file. So if you see over here, we are calling the I have just put it, I have not put it in all, I just put it in one environment and agent. You can put it in many components and can look at it. Just for the showing, I have put it. So you see that the environment is starting the build phase. Okay, so if you look at it over here, it is showing that's a UVM info message, and from this particular file called urtnv.svh, showing the line number at timestamp 0, showing the overall hierarchy. The hierarchy constructed so far is the UVM test top, correct? That's the name of the handle that we talked about, .menv. So menv is the name that we have given, but the UVM test top is the name UVM itself has picked up, and then ID is urtnv, and then it is saying build phase starting. So the build phase, so this is the display statement that I had added, and it is showing that this is happening first, which is environment is happening. Next, if we look at it in the order, it is saying agents, APB agent.svh, some line number at time 0. The build phase starts at time 0. And it's saying UVM test top, the hierarchy has now become extended. So it has menv, apb agent, ID is apb agent, and then build phase is starting. So you have the environment build phase and then you have the agent build phase. So with these two, I am showing you that it is really moving top down. So UVM framework provides the configuration database, and that allows for the storage and retrieval of data. In the build phase, typically what happens is any of the configuration objects are created and they are passed passed across to the lower level hierarchy, and then the lower level hierarchy, before doing their build, uses this configuration to make sure that it is satisfying the test intent, right? So somebody can say, I want interface with these many ports and all that. So from the top level, that gets that gets passed down to the agent, and the agent who is instancing so many, let's say if he has to handle multiple drivers, and if he wants to, or the environment wants to handle multiple interfaces, then he can instance multiple versions of those agents based on the information coming in from the configuration. So this way the main configuration gets created in the test, and then it is set through the configuration database, and then the lower level components, before doing the build, they will extract that particular configuration object and then use the structural configuration information from that high level configuration, and then start the lower level build and pass the additional configuration information that is relevant for the lower level component again through the configuration database, right? And then the lower level objects will do the same thing. They will extract the configuration object, look at it, and then build according to the intent that is specified by the test. So this is something that you will be able to see in like what exactly, how does the code look like, all in the context of the UR test bench. So other subphases of the build, the primary build phase, are connect phase and the end of elaboration. So connect phase is used to make a TLM connection between the components and then assign handles to the test bench resources. And this works from like a bottom up in the hierarchy. And just put the simulation log file to show you that like if you look at these two messages, it's first the agents connect phase is executing, and then the environment is connect phase is executing, showing that it is going bottom up. So generally your TLM connections are done over here. Test bench resources meaning like let's say RAL model, or it could be a global state object, or it could be virtual interface connections. All those are test bench resources. All those assignments are also done as the part of the connect phase, because the object becomes available only in the connect phase, right? In the build phase they are still being constructed, and there is no guarantee within the build phase as to at what point what objects will be available. So you don't do the object assignments. Only in the connect phase you are 100% sure that all the objects have been constructed, and then you can reference them without any fear of null object references. And then comes the last phase, which is in the overall build phase. The last one is the end of elaboration. You can make any final adjustment to the structure, configuration, or connectivity of the test bench if you want, because it's all dynamic, so you can still tweak and tune it. And its implementation can assume that the component hierarchy and their connectivity is in place. So in the build phase all have been connected, in connect phase all have been in the build phase all have been built, and in the connect phase all of them have been connected, so their interconnectivity is in place. Now the overall test bench hierarchy is in place, and it's now you can do any minor adjustments that if you want. And this also, I think most of these phases they all execute bottom up. So end of elaboration executes bottom up, and this is a function. So all of these are functions so far. Okay, before we move further, let's summarize few quick points. So what happens what happens is that run test causes the UVM test object to be created, which is named as UVM test top. Then its build phase is called. That's how the top-down phasing begins. And the test build phase causes the UVM environment to be created, which adds to the list of the components that we talked about. And then once UVM tests build phase returns, the UVM looks, when we say UVM root looks for the additional components, and then so it now sees the UVM env, and then it calls the env's build phase, which creates agents, etc. And then after the environment's build phase ends, it finds the agent components and then goes ahead and builds them, so on and so forth. It keeps building them till it sees no other new components. Until all the component build phases are called, and then once that has been done, the entire journey has been done, the UVM continues and then calls the connect phase. Now in the connect phase, just want to distinguish these two terms, because I think some of the names are very close, so that's why I'm sort of bringing this differentiation out, that the connect that we do with the TLM ports that you have seen is not same as calling connect phase. I know that might appear obvious, just to clarify it. So connect, when we say, like for example, we have been saying some component dot analysis port AP dot connect, and then we are passing some export to it. So the connect builds the database of connections to be made between components, and the order that you call connect method does not matter as long as both the ends of connection have been constructed, right? So as long as the two objects which are getting connected, as long as those two objects are present, then the order in which that you do connection between them doesn't matter. Okay. And all the connect calls have to be made before the end of connect phase. This is a very important point, that all your component connection you have to do it in the connect phase, because that information gets stored in that connection database, and that gets utilized, and that update to that database opens up only in the connect phase. Now you could call connect method during the build phase or the constructor, as long as other requirements are met. Other requirement meaning as long as those objects are available, then you can call connect within the build phase. Okay, that is possible. We are talking about connect, we are not talking about the connect phase. Right, so we can call connect, and the connect phase is a virtual method of UVM component, whereas connect is a method of UVM port base. So these are few points that sometimes can confuse. So this is the sort of the summary to clarify them. So we'll continue in the major three phases. I think like we have looked at the functions that are present within the build phase. Now we will go to the run phase. So first part of the run phase is this start of simulation, and this function occurs before the time consuming part of the test bench begins, and then it's intended to be used for displaying banners. Like sometimes you will see, like, you know, some people do the ASCII art. So those banners can be displayed over here, and then the test bench topology can be displayed because the entire test bench is created. UVM provides a built-in function print topology to print the entire UVM topology, the test bench topology that has been constructed as a part of build phase, and the configuration information that we are utilizing can be printed over here. And then sometimes what happens is, like, there is a system C based synchronization or communication, or there can be sometimes they also run like external processes. You know, you will see when you go to the advanced technique, like when you start doing some SOC simulations and all that, like people could be running a driver type of a code as an external process, and that communicates with the test bench to do something. There are various things people do depending on the requirement. So if you have to start any external tool that needs to start communicating with the test bench, those can be started at the start of simulation, because the real action is about to begin, and this also executes bottom up. So I think apart from build, which goes top down, rest all function based phases execute bottom up, and run, which is a task based, runs parallel. So this you can just remember. Then used. So now I'm moving on to the next part of the major run phase, which is the run phase. So after the start of simulation, executes bottom up till it has executed up to test. It goes into the run phase, used for the stimulus generation and checking activities, as well as the coverage gathering. Run phase is a task that consumes the time, and all forever type of functionality that is present in the component is implemented or forked off in this particular phase. Again, sort of reiterating, execute everything of it is executed in parallel, and then this concept itself is sort of carryover from the OVM type of a methodology that we had seen in the evolution. So one is that the run phase task itself gets called. Along with that, you have these sub phases that also run parallel. The sub phases are, you have reset phase, configure phase, main phase, and shutdown phase. And although like for example, looking at it, you know, this might seem very attractive, but the recommendation is that you stick with the run phase. But still, we'll look at what happens. I hope the point that these things are happening in parallel is clear. The reason for us to know about it, although the run phase is recommended, why are we looking at it? The reason why we are looking at it is there could be some environment that could be still using this. They might have a reason for it. Doesn't mean that it is useless, right? So we need to know about it, and in those, if they have implemented their sequence in the main phase, then we should not feel confused. That is why we want to understand this. So this is the order in which it progresses, but this order gets launched in parallel with the run phase, and we have to use only one of these. Either you use the entire run phase task, or you shift to this subphase, this main 4 subphase type of a flow, right? You have to stick with one of them. So these are 4 and their corresponding pre-post variants lead to a total of 12 new phases which are introduced in the UVM, and they execute in order. They are created to provide the finer granularity of control in the run phase. What happens is that while people implement run phase, they typically tend to do these things. Okay, so they tend to do like a reset, configure, main, and shutdown type of an activity they will do within the run phase. So now what they have done is they have separated out so that the intent can be made more clear, right? That is the one of the idea. So these run in parallel to the run phase task itself. So either you choose run phase and not both. Typically meant for tests and environment, and not for the other components. So within the test and environments, you can use these. The other components, it doesn't apply much. The reset phase can be used either for generating the reset to DUT, or waiting for an external reset to deassert using rise and drop objection mechanism. So each of these are task based phases, and as they run parallel across, when they say run parallel across all your components, right? So now there are two level of parallelism. One is the run phase is running the individual one, and the sub phases are running in parallel within a component, okay, and then across components these are again running in parallel. So just keep that picture in your mind, okay? So don't, like when we say parallel, now both the parallelism are there when we are talking about these sub phases, okay? So but since we are talking about subphase, we should not be worried about the run phase, right? So we are only talking about this, okay? So these phases, the sub phases of the run phase, are running parallel across all the components, and within them they run in order, right? That is, first reset phase will run, and then configure phase, and main phase, and shutdown phase. And how do they ensure the order is, how do they ensure that they move from one phase to another phase when they are running this parallel task based phase mechanism? It is based on the objection. So in every one of these tasks you can call objection, and when the total number of objection counts for that particular phase becomes 0, the phasing moves to the next phase. So in the reset phase, what you can do is you can actually take a reset interface, right, and then you can drive reset to the DUT from this particular phasing. So that is possible, and some of the test benches will do that. Or a reset could be generated from external TB top, the way we have been doing in the past, right? Like you assert the reset, wait for few clock cycles, and deassert it, and then in the reset phase we can wait for that particular reset signal. So the way you will do it is you will raise the objection, and then in the main, whatever, like in either in your test or environment component reset phase, you raise the objection, wait for that reset to get deasserted, and then you drop the objection. So that way when it moves to the configure phase, we definitely know that the reset has been deasserted. And then in the configure phase, you can configure the DUT registers and program any memories that can be done in the configure phase. And in the main phase, you actually start the stimulus generation, checking, and coverage gathering process. And in the shutdown phase, you ensure that the effects of the stimulus generated during the main phase have propagated through the DUT, and any resultant data has drained away, and can execute time-consuming sequences that read the status register. So the final thing, you can do it in the shutdown phase. So in the main phase, you can generate the stimulus, and in the shutdown phase, you can wait for all the responses to be flushed from the DUT, right? So you could check for some status registers, or you could even make your scoreboards wait for all the response collection. So that can be done as the part of shutdown phase. We will look at this a little bit more detail when we go to the end of test criteria. So all pre and post are used for each of these reset phase, configure phase, main phase. We have those two pre and post phases. Those can be used for tuning the corresponding phases. So that is the overall way these phases can be utilized. So that completes the broad run phase. So we have completed the build phase, broad run phase, and we looked at the sub phases as well. Now we are coming to the cleanup phase. So in the cleanup phase, the first function to execute is extract phase. So here you retrieve and process information from scoreboards and functional coverage monitors, and typically this is used by the analysis components, right? So analysis components are primarily your scoreboards and checkers, and the coverage monitors. And then in the check phase, you post the test execution checks for the intended behavior match, and then again used by the analysis component. So whatever you have extracted across all the components, you have extracted the information from them, and then sometime you might have to cross correlate the information across them. That you can do it in the check phase to see whether the whatever the test intent that you had, whether it has met. Okay, so many transactions from this interface, or whether they have come out here, how things have overall happened, you can check that. And then in the report phase, you display the results of simulation, like saying whether the test has passed or failed. You can write some of the statistics and the information like that to the other files as well, and then you finally display whether the test has passed or failed. And then comes the final phase, wherein any files that had opened, or sometimes for transaction recording type of a feature, you can record it directly in a database SQL database you could be recording, all those databases can be closed. And then as we talked about at the beginning, there could be an external tool that we would have launched which is communicating with the simulator to do some extra processing. Such they are called as co-simulation engines. So if you have launched any such co-simulation engines, you can terminate them in the final phase, and all cleanup phases again they execute bottom up, right? So that I think is the summary. So build is top down, connect is bottom up, run is parallel, and all rest of the phases they execute bottom up. Okay, we have looked at so far, like we have started how the test has begun, how it has gone into phasing, and then how it executed all those three major phases, the build phase, run phase, and the cleanup phase. Now we are coming into, like for example, how does the end of test ties in with it, right? So we talked about it briefly. Let's look at it because it's an important topic to be understood. So end of test, what this means is that we need to make sure that at a very simple level, right? Like if you remember in our verification introduction session, we had said the stimulus, we had talked about verification is about two things, right? So we had talked about even our verification goggles. So it is about generating the stimulus and doing the response checking. So any end of test means that all the stimulus has been generated from your test bench, and then all the responses to the stimulus that is provided to the DUT has been received, right? Because we need to check that. Unless we check it, we cannot say test has completed. And how do we do this, right? So the test is the component that is generating the stimulus, and it generates it in the run phase or the sub phase of the run phases, which is the main phase. And then run phase or main phase should not end till all the stimulus generation has completed, and typically this is managed with the objection. So we, like, let's say I have a class pipeline test in the run phase, which is a task based thing which consumes time. Only in those phases, the task based phases is where the objection mechanism is applicable. You can say phase, which is the object that gets automatically passed while calling these phases from the UVM. You say phase.rise objection, and when you do this, what UVM ensures is that unless this particular phase across all the components, the number of objections becomes 0, it won't move to the next phase. So that is what your UVM phasing engine will ensure. So then I say pipeline sequence dot start, and as we know, this is the blocking function call, and it will generate all the stimulus, and only after all the stimulus has been generated is when this sequence will complete and come out, and then we'll say phase.drop objection, and then the test will complete. Now a question might come in your mind that, hey, like if I've generated all the stimulus, why will there be any left out? The key thing to note over here is, so if sometimes let's say we are sending a data, and then if the DUT consumes that data completely at that point of time, it is the end of transaction, then there is no problem. This, what we are doing is more than sufficient, right? It has processed the last stimulus that we sent it out, DUT has consumed it, and it will indicate whether it has done it successfully or there is any problem immediately, right? Like even if we take a simple APP type of a bus, I issue a read, it will give the data phase, and only after the data phase has been completed is when my read sequence is completed. So beyond, after that completion point, there is nothing to do with the DUT. We are done, right? So that all the communication is completed. If that is the nature of communication, then it is sufficient, because within that everything is built in, right? The transaction is atomic in nature. That is that it all its phases gets completed, it's over, there is nothing else to be done. But the complex designs are not like this, right? So the most of them are sort of pipelined, and when you have the pipeline type of a design, what happens is you send multiple requests, and then when you generate them and give it to the DUT will take some time, because it has several stages of pipeline built within the DUT. It won't give you all the responses immediately. So when it doesn't give you all the responses immediately, what happens is your stimulus sequence would have completed, but I means the test bench has not received all the responses, so I need to wait for it, right? How do I do that? That is the next problem. Let's look at it. How do we address that? So one way that we can do is, let's say we figure out, what is the total time required to drain out all the responses out of DUT for the stimulus provided, and let's say we come up with some number. I've just used, like, let's say I've tick defined a drain time as 1000, and if I extend the same test, what I can do is I will say pipeline sequence dot start, and that will ensure that all the stimulus is generated, all the requests are sent out. Now I will wait for like a drain time, right? So when I wait for the drain time after generating all the stimulus, that means the responses will be received, right? And processing response is not the responsibility of test. There are other components. The monitor will monitor, send it to Scoreboard, Scoreboard will check. All that mechanism is put in place. The test itself doesn't have to worry, right? Because we have a self-checking environment. That's the value proposition from the UVM. So test doesn't have to worry. It just has to generate the stimulus, and then it is waiting for this drain time to ensure that for all the stimulus that it has generated, the response from the DUT are flushed to the test bench, and then it is dropping the objection. So this is the bare minimum that you need to ensure that if you have a pipeline DUT, you are giving time for the responses to come in, right? But now what happens is that there are few things, right? So one is that I will have to do this in every test, right? Depending on what type of stimulus that a particular design is generating, I might have to sometime tune the delay as well. But let's say I take the maximum delay and put it. I don't worry about the performance, simulation performance. I am willing to spend some more machines and licenses because that all costs money, right? But let's say I am rich and I'm willing to spend it, but still I have to go and add it in every test, right? And that's a extra expense for me. And then after so now that's one problem, right? So I have to go and add it in every test. So what I can do is instead I can use the there is a drain time mechanism that's provided within the UVM that I can use it. So what it does is in the run phase, after all the objections have been dropped, the simulation end can be delayed by specifying the drain time, right? So the way you do it is you can call at the end of your elaboration phase for the run phase, right? You can see that for the run phase we can set the drain time, right? So we can set the drain time saying whatever the drain time value that we have. So we are saying UVM phase, run phase, and we are saying UVM phase scope resolution operator gets you the run phase object, and for that run phase we are setting phase done dot set drain time. We are setting it to the drain time that we have specified, and this we can do it as a part of your base test, right? We don't even have to do it in every test, so we can do it in the base test, and then every test will be able to get it, and the UVM itself will delay the run phase completion by this time even after all the objections have been dropped, and this provides the ability to flush all the responses from the DUT. All good so far, but what can happen is that the drain time can keep changing depending on the type of stimulus, and then the design can undergo changes, the pipeline stages can change, and so what happens is it can sometimes lead to false failures, right? Because the drain time has become short, and because of that there could be false failures because more response were expected to come and they didn't come. So the right approach would be to really wait for all the responses, right? And how we can do that is we know that our scoreboard component is tracking the number of requests and it knows when all the responses have come in, right? So we can extend the simpler way is that we extend the objection mechanism to scoreboard as well. So far we are making only test participate in the objection mechanism. So now let's say we make the scoreboard participate as well, because scoreboard knows like every time it receives a request that has been generated from the monitor, it knows the expected response that are supposed to come when I can say that this request has completed, right? And I can then say whenever a scoreboard has received a request, I can raise an objection, and then I can drop the objection when the corresponding response comes back, right? Because the problem with the good thing about scoreboard is it knows for any given request how many responses are expected, but the problem is that the scoreboard doesn't know how many requests are going to come, right? Because it doesn't know, it's not generating the stimulus, so it can't just raise the objection, and we cannot say, okay, if I'm generating 100 requests, then raise the objection once and then drop after all the 100 requests response have been received, because scoreboard doesn't know how many of requests you are going to send. So scoreboard has to do it at a transaction level. So the moment it has received one transaction, it can raise it and it can drop when the corresponding transaction has been satisfied. Okay, it cannot do it at a level of entire thing put together. So when we do that, the recommendation from methodology is that leads to a lot of performance hits. These mechanisms although look really good, like objection mechanism might really look good, but everything costs simulation cycles, correct? So if you do that rise and drop objection at every request, every transaction level, then it takes a lot of simulation hit, and your overall test execution speed will get affected by it. So what do we have to do about it? So for checking that all the responses have come in, we wanted to do the the rise objection and drop objection from the scoreboard as well. But the problem that we foresee is that then we'll have to do it at every transaction, and that takes a performance hit. So the solution that is typically used is every UVM component has this function called phase ready to end that is called before the phase is stopped. Okay, and it's invoked when all the objections to ending the given phase and all sibling phases have been dropped, and thus indicating that this particular phase is can do a clean exit. And it's called for all task-based phases, which are primarily the run phase and its subphases. And as we have seen, the general recommendation is that you use the run phase and not the subphase. And we have to keep in mind that the phase ready to end is a function. It's not a task. It gets, although it gets called for the task-based phases, but it itself is not a task. It's a function. You cannot put a time-consuming functionality in over here. And the way you do it is you use a fork join none type of a structure, which is allowed in the function, and we can implement a small logic with the fork join none to make it wait. So what we will do is in the scoreboard, we will add this functionality called phase ready to end. We will populate this particular function, and we will populate this particular function for the run. So if we say phase dot get name not equal to run, it's not called run phase, the phase name itself is called run. Then we just return, and when there is a run phase that is about to exit, we look at if outstanding request queue size is not equal to 0. So let's say that in a particular request queue we have been tracking the transactions for which the response is pending, and then whenever the response had come, we were, let's say, popping the requests from this outstanding request queue. We check the size of that guy. So at the end of the run phase, or okay, at the end of run phase, test has dropped its objection. So after the test has dropped its objection, the phase ready to end has been called, and we have looked at that it is a run phase. Run phase is a phase ready to end call, and within that we are checking that the outstanding request queue size is greater than or equal to 0 inside the scoreboard. Okay, so we are looking at it inside the scoreboard because we are interested in waiting till all the responses have come in. Okay, so if we find that there are requests pending, then we say phase dot rise objection. Now what we will do is we'll do this, and then we say fork join one, we delay the phase end. Okay, we call this delay the phase end, and we say join none. So we are doing join none, right? So that way we are not really waiting in the context of this particular function. So this function will complete, then we go to this particular task, and in this particular task you can see that we are waiting for the outstanding request queue size to become equal to 0. Okay, so we are waiting for this, and after this becomes equal to 0, we do the phase dot drop objection. Okay, so we do the drop objection. We had done the rise objection in the context of function, and we had forked off this particular thread with the join none, which is legal to do within the function. And after doing that, we are waiting for the delay for the phase end, and then we are looking at that the all outstanding request queue has become 0. That is because now as we wait, right, so all the responses will come from the DUT, and once they have come, every time a response comes, I am removing the corresponding request from the queue, and after a final response comes, my request queue will become 0. Until that I am holding the objection. So now this will make sure that your run phase gets delayed, and then I will drop the objection, and then I will move on with the next phase, right? So that's one way to delay the run phase till all the responses have come. Now here also again we have one more small problem, that like if there is a bug in the DUT and let's say it doesn't issue one response, right? So then our outstanding request queue will never go 0 and the test will hang. So what do we do in such case? Let's see what needs to be done in the next slide. So when let's say some response doesn't show up from the DUT, and then to avoid test from waiting forever, the UVM provides a mechanism called global timeout, and this global timeout is set to like 9,200 seconds. So if something goes wrong and the objection has never dropped, then what happens is after the UVM timeout value, the simulations are automatically terminated by the UVM, and this value can be changed using plus UVM timeout equal to argument. Here you can pass two argument. You can pass the value of the timeout that you want to change from 9,200, which is the default value within the UVM, to whatever the value that you want. Let's say I want 1 second, 2 second, whatever, right? So whatever that you want, you can pass it over here, and that's a simulation time I'm talking about, of course. So allows the users to change the global timeout in the UVM framework, and the additional argument you can pass it as yes or no, and if it is set to no, then if the user code tries to change the global timeout, then a warning message will be generated. Then what we have to do is there is another mechanism or two mechanism. Let's say you don't want to pass it through the command line argument for every test. You want to put it in the base test itself. You can populate the start of simulation phase, and you can say that like a UVM top, which is a handle of your UVM root. You can say dot set timeout equal to whatever the value that you want to set it to, right? So you can set that to like 1 second, for example, using this particular call, and so you can change the default value by calling this set timeout function. And let's say you do this, and as well as you pass UVM timeout, for example, then what happens, right? So what you have to note is the UVM timeout argument gets parsed during the build phase. So if both of them are passed, and if there is if this particular the other argument is not no, then the UVM timeout value will be overridden by this, because in this particular case I am setting it at the start of simulation. But there is one challenge, however, that there is no way that you can implement an ideal type of a like a global timeout value, because you don't know, right? So this is something that you will realize as you start looking at more complex projects, that it's very hard to define a good timeout value, right? Something could become a very large, in which case a test has to fail, but you are unnecessarily waiting for that particular duration of time, or something that fails in a false way before we have given the enough timer value. So the solution for that problem is to use this concept of watchdog timers, and the idea of watchdog timers is that you start monitoring the activity of all your DUT interfaces, and if there isn't anything happening from your DUT interface for whatever the duration that you have specified, then you can say that that the DUT is hung, and then terminate the simulation. Basically, when the response has not come back, it's a bug and it can lead to hang, and then that hang you check it using watchdog. So watchdog, you can just imagine that literal term, it's a dog watching the DUT, watching all the interfaces. So one very simplest example I'm showing how you can do it, right? So at every passage of clock, you are watching the activity from the DUT, and this activity is a combined activity from all your interfaces, right? So in some way you define activity for every interface, and if you see that activity, then what you do is you reset a counter, and if there is no activity, you keep reset the counter by loading the max value, and if there is no activity, you keep decrementing that particular counter, and if the counter reaches the value 0, then you say that the timeout is equal to 1, and then that can trigger a UVM fatal type of an error using the watchdog timer. This is a very basic concept I am demonstrating, but essentially the same can be extended. Even you can implement such a mechanism within the class-based mechanism as well, by taking every agent can provide if the interface is idle, right? So you can take all such idles together and see that if all the idle are like holding good for a long duration of time, then you can say that there isn't anything that is going to happen, and then you can flag a watchdog timeout error. So these are the various mechanisms that are available for you to implement the end of test and solve the problems associated with it. So there is this one advanced concept with respect to phases. It's called phase jumping, and so what happens is that the typical UVM phasing flow will go in whatever the order that we have defined. It goes from that build, run to the cleanup phases. But if you want a certain phase to end prematurely and you want to go to different phase from that phase, then you can do so. Okay, then the overall order you are controlling, the user can control it, and you can go somewhere else in the schedule. All that can be done. One of the use cases, although the dynamic resets in the middle of traffic can be handled in a different way, so one of the ways to do that is to use the phase jumping. So this can be done. So I'm showing you like one very brief example. This is not to give you the complete sort of solution that involves far many more considerations and the nuances associated with various cleanups and stuff like that that has to be done. It's not just the phase jumping is not going to solve the dynamic reset handling. I'm not solving the dynamic reset handling problem over here, but I'm just showing you sort of how the phase jumping can be utilized, and moreover showing, I'm just introducing you that this concept exists so that in future if you need to find out more, you know that yeah, you know, this exists and you can explore more about it. So here I have a run phase, and then in the run phase I am raising the objection as usual. I'm generating the stimulus. This is the tests run phase I'm doing, and what I'm doing is I'm waiting for a reset, right? So I'm waiting for a reset, and if the reset comes in, I am saying that yeah, the reset is detected, and then I am saying phase dot jump. This is all the built-in calls, and I'm saying I can jump it to pre-reset phase, right? So I can jump to any phase from here to, I mean, it's up to you, but you should be aware and your environment should be capable of dealing with it. That is what is important. So it has to be adjusted all around, and so once you do this, then it will terminate this particular phase prematurely and go to again the pre-reset phase from which it will continue executing downwards, right? So that is a type of capability that is provided within the UVM. It should be done at a very, as we talked about, should be done at a very advanced stages when you have very good understanding of what you are doing. Otherwise it can mess up a lot of things. Okay, so this concludes this session on phasing. So we have started from the test beginning, like how do we do the entry into the test, and then from there how we create the test top and enter into the phasing, and how do we execute all these three major phases, which are build phase, and then your run phase, and then the cleanup phase. And within that, how we have these multiple sub phases, and what do we do in the build. We are building the entire environment top down. Why it has to be top down, we have looked at it. Connect phase, how we did it bottom up, and then when we came to run phase, we looked at how there is a two different level of granularity that is available. At a much lesser granularity, we have a single run phase which we have gotten from the OVM, and UVM has defined or divided this into 12 sub phases that we looked at, and then we understood that only one of them should be utilized. And then the run phase runs parallel, and moving out of run phase to the cleanup phase is based on the objection mechanism. All the task based phases can utilize an objection to hold the particular phase. So it moves out of that phase only when the objection counts across the components had dropped to 0. So we looked at briefly about that, and then we looked at the cleanup phase, and within each of these functions what needs to be done, that we have understood briefly. The overall we have understood that build goes top down, connect goes bottom up, run is all parallel, and rest of the function based phases are all bottom up. I think that is an important point we have understood. After ensuring like how do we do the start, how do we enter the phasing, how this goes through sequentially, we looked at the end of test problem. So end of test problem wherein we have to wait till all the stimulus is generated, all the responses have completed, and the simple objection mechanism can be used for the stimulus. But for the checks, we found that we need to, so for pipeline design, we have to wait little longer so that all the responses can be flushed out of the DUT. And in order to do that, we initially started off with a very simple approach of set drain time, right? So which provides us the additional time at the end of, like for example, run phase, any task based phases, I can set the drain time so that at the end of that phase it waits additional time after all the objections have been dropped. So that allows us to get all the responses in place. But then we figured out that the fixed delay type of an approach can never provide a foolproof approaches. So the way you have to do is depending on the situation you evolve. For a simple one, the drain time itself might be sufficient, but as the DUT complexity goes up, you will have to go through the other mechanisms that we talked about. So in the other cases, you can make the scoreboard also participate in the the objection mechanism. But we figured out that scoreboard operates at a transaction level, and if it at every transaction level it does the rise and drop objection, then that's going to be a problem for us in terms of the simulation performance. So we figured out that we can use wait for phase end and then wait for the run phase to end, and the wait for phase end itself was a function, but we used the fork join none to like raise the objection and then go wait for all outstanding responses to come in, and after that we do the drop objection. So that is another way we delayed the run phase from dropping the objection before moving to the cleanup phase. But along with that came the problem that we could have potentially the DUT may not send any response, and because of that the test can remain hung, and how long to be wait. And then there we saw that UVM provides a global timeout, but we saw the issues with the global timeout. In general, with any fixed delays cannot adapt, right? That is the main problem. It exists as the initial point to start off with, but as you go further you have to optimize it. And the way to optimize it is we looked at a watchdog timer type of a concept, wherein you look at the DUT activity, and if there isn't any activity for the duration that is specified, then you say that now we don't need to wait any longer. Even if there are outstanding responses, we say it's a watchdog timer timeout, and we move on and terminate the simulation. So this is for the better simulation performance. So that was the overall idea of how do you detect the end of test for any given test. And we briefly looked at phase jumping, which is an advanced mechanism wherein the sequential way of things happening, the running through the phases, different phases, how that you can affect using the phase jump. And we looked at a very simple like a partial solution of how to use the phase jump to handle the dynamic resets in the middle of the traffic. Of course, that was not a complete solution. It was just a sort of partial demonstration from the point of view of how the phase jumping can be utilized. So this is the overall view of the UVM phases, and thank you for listening.